How quickly is our universe expanding? This is regarded as the most fundamental question regarding the cosmos, and scientists have been debating it for decades. Everything from how galaxies develop to how they might eventually drift away depends on the pace of expansion. Our entire conception of the cosmos, its age, and its ultimate fate is shaped by the Hubble constant, a figure that represents the universe's rate of expansion. Before diving deeper, let's consider why the expansion rate, called the Hubble constant, is so crucial. Named after Edwin Hubble, who first observed that galaxies are moving away from us, this constant helps us map out the history and future of everything we see in the night sky. Determining it with precision has been a major goal of astronomers for decades. When the Hubble Space Telescope was launched in 1990, one of its main objectives was to pin down the universe's expansion rate. Before Hubble, estimates of the universe's age ranged wildly from 10 to 20 billion years, a huge uncertainty. Thanks to Hubble's observations of Cepheid variable stars that pulsate at regular intervals and serve as cosmic mileposts, we now have a more precise age of about 13.8 billion years. Despite the new data, the tension between measurements remains. The Hubble and Webb telescopes confirm one universe expansion rate based on observations of the local universe. Meanwhile, observations from the early universe, like those from the Planck satellite's mapping of the cosmic microwave background radiation, suggest another. This leaves cosmologists scratching their heads. Is there something about the fabric of space we don't yet understand? Does resolving this discrepancy require new physics, or is there another explanation? In October 2024, as reported by NASA, Brenda Fry from the University of Arizona and an international team took a different approach. They used gravitationally lensed supernovae to measure the Hubble constant, a method independent of previous techniques. While observing a densely populated cluster of galaxies, they noticed something unusual. What are those three dots that weren't there before? Could that be a supernova, the team wondered? It turned out to be a type supernova, an explosion of a white dwarf star, magnified and split into multiple images by the gravitational lensing effect of the intervening galaxy cluster. Gravitational lensing is important to this experiment. The lens, consisting of a cluster of galaxies situated between the supernova and us, bends the supernova's light into multiple images. This effect not only magnifies the supernova, but also allows scientists to measure the time delays between the images, providing another way to calculate the Hubble constant. Their analyses confirmed that these dots corresponded to an exploding star with rare qualities. So where does this leave us? The Hubble tension isn't going away. It might be telling us that there's new physics waiting to be discovered. Perhaps our understanding of dark energy, dark matter, or other fundamental forces needs to be revised. Could the solution lie in something entirely unexpected? Perhaps there's a new particle or force that affects the expansion rate, or maybe the nature of dark energy changes over time. Some theories even propose the existence of extra dimensions or modifications to gravity at large scales. It's also worth considering that the universe might not be uniform in all directions. In the end, the universe is reminding us that there's still so much we don't know. The quest to figure out how fast our universe is expanding has led to some fascinating discoveries and even more intriguing questions.